Okay, so in this chapter, we have rotation, rolling, torque, and then we still borrow the concept of energy conservation. So this problem puts a lot of those concepts together. Okay, so here I have a meter stick, okay, pivoted about a point, okay. So this could be the same as if you're just holding, let's say, the eraser part of your pencil, okay. So you're holding that on the table, tip of the pencil is pointed toward the ceiling. You're still holding on it, pinching it with your fingers kind of lightly as you let it fall toward the table. Okay, so the meter stick, mass M, length L, pivoted about that end, I'll call that axis A, released from rest. Okay, so, whoops, so I'm going to call omega initially equals 0, so released from rest. And then when it reaches the horizontal position, now this doesn't have to be a floor. Okay, that doesn't have to be a floor. Okay, this could be just someone pivoting the stick, okay, maybe 10 feet off the air or 6 feet off the air, and this thing is just going to keep on moving in that direction. Okay, so yeah, it's not necessarily hitting the floor. So when this thing's released from the vertical, I want to know the angular speed and the angular acceleration at the instant the stick is horizontal. Okay, so as the stick falls from here to here, okay, I want to take a snapshot, click, right there when it's horizontal. Okay, so I want to find the angular speed, that's omega, and I want to find the angular acceleration, alpha. Okay, so the book doesn't really do a good job of explaining what they're doing. I think in an earlier edition they may have, and they may have kind of swapped some things around. Okay, I think they left a couple things out. Okay, so what's happening is, and eventually we're going to do a similar problem soon, where we're going to have a ring. Okay, have a little pivot point here. You let go. Imagine it's a ring or like an empty roll of tape. Okay, just put your finger here and pivot it there, and you let it go, and this thing's going to swing back and forth like a pendulum. Okay, so we're going to be looking at the center of mass as it goes high and then low and then back high and low. Okay, so this is how we're going to deal with this. Okay, so what's happening is the stick is going from one energy state to another energy state. So what type of energy does it have initially? Up here, potential. What type of energy does it have over here? Okay. What, with respect to that horizontal, it would have kinetic. Now, if we talk about potential energy, okay, right, you know, potential energy is mgh, all right? Well, which m and which h? Because all different chunks of the meter stick, there's some mass there, there's some mass there. All different parts of the meter stick have different heights, okay, above the axis of rotation. So what we do, because we looked at the center of gravity, we showed that the center of gravity is the point where the net torque due to the weight acts. So we're going to inventory the height of the stick by where its center of gravity or its center of mass is. Okay, remember, for our problems, the center of mass, center of gravity is the same because little g is constant over the size of our object. Okay, so we're going to look at what does the center of mass do. Okay, so here's our energy expression. This work done by are there any non-conservative forces that act? Well, yeah, okay. You've got the support force, which would be a normal force, okay? But as that stick rotates, that normal force is not acting over any displacement. So that normal force does no work, okay? So that's 0, no energy loss due to friction, so energy is conserved. Okay, so I wrote initial potential, initial kinetic, and same for a final. Here's my reference point for potential energy. Okay, here's my reference point for potential energy. Okay, so the initial energy is all potential. Okay, initial potential energy, that's mg, and we look at the height of the center of mass, that's L over 2. Okay, initial kinetic's not moving. Final potential, 0, based on our reference point. Final kinetic. Okay, so this stick, okay, remember, total kinetic energy is a rotation about the center of mass plus translation of the center of mass. So this stick is purely rotating about the pivot point A. So the only type of kinetic energy is rotational kinetic energy about the pivot point. Well, that's a stick about one end. So the moment inertia is our 1/3 ml squared. So my 1/3 ml squared, okay? And let's see, I can get rid of the m's. I can get rid of the 2's, okay? And I solve that for my angular speed. So when that stick reaches the horizontal, that's my angular speed for part A, okay? Now, to find the angular acceleration, okay, all I'm going to do, okay, again, I want to find the angular acceleration when the stick's at the horizontal. So what I do is I just draw the stick when it's at the horizontal, okay? So here the stick's moving, right? Remember, started up there and it fell, okay? So the stick's moving. And I want to find alpha, okay? Now, if I go back here, remember this omega, okay? That's omega for every point on the stick, okay? So that's a good point. Let's go back here, okay? So this is chunk M1, that's chunk M2, right? That's my ith chunk. If you look, all of these pieces of mass, okay, they all went 90 degrees. Remember, omega is delta theta per time, okay? So that's another way to look, to realize that every part of the stick has the same omega. Okay, obviously not the pivot point, but every part of the stick goes 90 degrees in the same amount of time. So there's only one omega, and likewise there's only one alpha. Okay, because remember, alpha is change in omega with respect to time. Okay, so there's only one omega, so there's only one change in omega. Okay, so I want to find alpha. So we're going to apply F equal ma in rotational form about the pivot point. Net torque equals I alpha. Okay, so you have to draw the forces that act on the stick at this orientation. Well, you have the support force. Okay, you have the pivot point. Okay, so that's a normal force. So this would be like if you had a meter stick and you had a hole drilled and you put it on a nail, right? That would be your normal force. Okay, that's the support force. Okay, and then I have the weight of the stick. That's the only forces that act on the stick. So I'm going to apply net torque equals I alpha about my axis of rotation. Okay, now the stick is rotating clockwise. So that's my positive direction for alpha. Okay, remember I said that the book always says that counterclockwise, like in geometry class, counterclockwise would be a positive torque. But I said that's not a good convention because in this problem, everything is rotating clockwise. So there's no need to make the direction something's going negative. All right, so I have my direction for alpha. So if I look at my net torque, the only force that causes the torque about axis A is the weight. So there's my force. Okay, remember, torque is force times moment arm. So there's my force. My moment arm are perpendicular. Okay, that's my half the length of the stick, L over 2. It's a stick about the end, which is 1/3 ml squared, right? So that's one of the ones we need to know. And then I solve that for alpha. Okay, so that gives me my angular acceleration of the stick. All right. Now, the odd result about this part, okay, I'm gonna scoot down here, okay. Okay, so again, this is the stick that started at the vertical and we let go and it was falling to the horizontal, okay. Now, if I had taken the same stick, okay, we'll go back up there, but if I took the same stick and I held it at the horizontal, okay, if I held it here, and then I let go, so it started here at rest, okay, I would end up with the exact same alpha, which is kind of strange, okay. So if I drew the forces on here, whoops, I didn't draw my normal force. So if I drew my forces, okay, I'm trying to find alpha, so I'm applying net torque equals I alpha about axis A. Okay, the only force that causes the torque is the weight. So there's my weight. There's my moment arm. Moment inertia about axis A is 1/3 ml squared, and I get the exact same alpha as that I had above. Okay, so the geometry kind of looks different. I mean, this stick is going from the vertical, whoops, going past the horizontal. It's moving. This stick starts out at rest. Whoops. This stick starts out at rest, and I'm releasing it, and the alpha is the same. Okay. Well, the reason is for this picture here, okay, and this picture here, the force diagram is the exact same. Okay. So all I have is normal force up, mg down. Normal force up, mg down. So in this picture here, you can't tell that the stick is moving. Okay, I just have two forces. Here I have two forces. Okay, so the state of the stick is the exact same in terms of the net torque, so you wind up with the same angular acceleration alpha. Okay, now another interesting thing is if I go back to this picture I had, here is the stick at the vertical. Okay, and it doesn't matter whether it's moving or whether I let go of it from rest. Okay, we just saw that alpha is the same. Okay, but if I look at the tangential acceleration at different parts of the stick, okay, remember tangential acceleration is r alpha, all right? So if I remember the tip of the stick is tracing out a circle, okay, so hence it's called a tangential acceleration. It's tangent to the radius, okay, tangent to the circle. So the tangential acceleration of the end of the stick is r alpha, where r is the length of the stick L. Okay, so what I did, right, I put in a tangential is r, the length of the stick, times alpha. Okay, so the L's cancel and I get 3/2 g. Okay, so that says that the tangential acceleration of the end of the stick is 50% more than g. It's 1.5 g. Okay, the middle of the stick, okay, at the center of mass, the tangential acceleration, a tangential, okay, r alpha. The distance out to the middle of the stick is L over 2, and alpha is my 3/2, there's my alpha, 3/2 g over L. So the L's cancel, and I have a tangential is 3/4 g. All right, so we just looked at this problem right here, and one of the results is that when I had a stick, like a meter stick, you could use a ruler, right? Just hold your hand under it, okay, kind of pivot it from there. And when you let it go, we found that the tip of the stick, the end of the stick, falls away faster than the center of mass of the stick. Okay, so the tip of the stick falls away with acceleration, tangential acceleration 1.5 g, and the center only 3/4 g. Okay, so I redrew that stick from here. All right. So what's happening is what we found is here's my stick, there's my pivot point. And again, you could try this with a ruler, just kind of pinch that. Don't pinch it too tight because there's too much friction. Just pinch it a little bit with your fingers. And you could put maybe a coin here, you could put a coin there, okay, or actually a pencil eraser there, okay, but in a pencil eraser there, okay, and then let it go. And as you drop it, okay, as the stick falls towards the table, since the end of the stick, falls away with an acceleration of 1.5 g or 150% g, okay, the stick starts to separate here, okay, so the stick now leaves, or I should say the mass now leaves the stick. So the stick is accelerating away quicker. So you're going to see a space here. Okay, so you can actually do that in front of you and actually see that space. Whereas the one that's sitting at the center of the stick at L over 2, its tangential acceleration is less than g. So as the stick falls, this object stays put on the stick, whereas this object separates from the stick. Okay, and I'll show you a video on that.
Rolling and action.
Okay, so here's an object that is, let's say, attached to the ground somehow, and it's made up of little chunks of mass, and it's falling. And so I went up on the object and I said, okay, this mass 1 is further away from the axis of rotation. Okay, so if I look at what path does M1 take, right, it's following a circle. Okay, so its tangential acceleration is in that direction. And then mass M2, a little bit closer to the axis of rotation, okay, it has a smaller distance from the axis of rotation, so its tangential acceleration is a little bit smaller. Okay, that's that one. All right, and they're not drawing the scale. I'm just showing that that one's larger. Number 1 is larger than number 2. Okay, well, Newton's second law says that if the tangential acceleration is bigger, okay, so is the tangential force. Okay, so the tangential force on number one, okay, also points in that direction, is larger than the tangential force on number two. Okay, so you have two pieces of the object that actually have two different sideways forces acting on them. So mass one and mass two, they could actually break apart and separate. Okay, so what would be some examples of that? All right. Well, let's say if I have a stack of blocks, okay, and you could actually do this at home if you had a stack of blocks or something like that, and maybe just use a little bit of tape. You don't have to use tape, but it works better if they're a little sticky. And you first start with them vertical, okay, you tip them over, and they're not going to fall all the way to the ground as one large row. They're actually going to start to break. So what happens is as these things are falling, you have these different tangential forces. That was my F1 and F2. Okay, you have those different tangential forces. And actually, going back to this picture, if these things are blocks and they can actually move on top of move on top of one another, you actually have a static friction force holding them together. And eventually when the tangential force overcomes the static friction force, then they can break apart. And then once it breaks apart right there, okay, and then this portion right there, okay, that becomes, right there, that becomes the end of now the new shorter stick. There's the shorter stick. And then the tip of that shorter stick right there, there's the end of it. That's now going to have a large tangential acceleration. And the upper portion of this stick, okay, the upper portion of the stick is now no longer connected right there. So the center of mass is going to be in free fall with acceleration g. Okay. Here's another example. Here's a stack of blocks, okay, start at vertical. It starts to tip, and it's not going to hit the floor as a stack of blocks. Eventually it breaks, okay? And right before it broke, okay, you had some tangential forces like that, and one was bigger than the other, and so this block, that block slipped from that block, okay? So the tangential force overcame the static friction. And then once the system broke, okay, it was actually breaking right there. Once the system broke, then that became the end of the new stick. Okay, there's your new stick. So it has a tangential acceleration that's different from the upper portion of the stick. So the upper portion of the stick, or the upper portion of the blocks that are stuck together, okay, their center of mass is there, and that system is going to fall. Well, they're all going to be in free fall. Okay, that system is going to fall with an acceleration of g, while the tip of the stick falls away faster because it's rotating. Okay, remember you have that normal force that's acting. Okay, so again, the bottom of this stick is not in free fall. It has a support point right there. Okay, or static friction is holding the bottom to the floor. Okay, so here's a chimney. So this thing was falling, okay? You have bricks, that was like the masses I drew, okay? You have differential tangential forces, which then rips the bricks apart, okay? What holds the bricks together? The mortar, okay? So that tangential force overcomes the strength of the mortar, then it breaks, and then now this becomes, okay? That becomes the new end of the stick, which falls away faster than the center of mass of the part that's left, which falls away with an acceleration of g. Okay, so the tip is going to hit the ground first. Okay, that part is going to hit the ground first. Same thing here. Here's another one. Okay, this one here, what's happening down here is this was one large smokestack. Okay, it looks like it broke here first. Okay, broke there first. So that became the end of the stick right there. So it had a tangential acceleration. And then that portion right there was in free fall. The center mass is in free fall. So it lags behind because the tip of the stick here is falling faster. Okay, it has a larger acceleration. And then as this stick fell, it broke right there. Okay, so now that became the new end of the stick that has a tangential acceleration, and that chunk right there is now in free fall, and its acceleration of the center of mass is little g. So the end of the stick here is going to hit the ground first, right there. And I'll show you some videos on that as well.
Timber. Whoa!